Okay, good afternoon, everyone. I think we can start. Thanks for coming to this new colloquium. Today, it's my great pleasure to introduce Charles Gammie from University of Illinois. So Charles did his PhD at Princeton University between 1987 and 1991, and then he moved to University of Virginia as a fellow, then to the Harvard Smithsonian Center for Astrophysics as a postdoctoral fellow and then a research associate before moving to Cambridge as a postdoctoral fellow first at the Institute of Astronomy, and then as a Rosenbaum Fellow at the Isaac Newton Institute. And then in January 1999, he get an assistant professor position at the University of Illinois, and is now, since 2005, a full professor at University of Illinois. He's a specialist of theoretical and computational astrophysics, and he received many awards, including some awards for his participation at the Event Horizon Telescope. So, for example, the Einstein Medal of the Albert Einstein Society. And today he's going to give us a portrait of black hole. That's for you. Don't forget to. Thanks.
All right.
Thank you.
Can you hear me? Can you hear me? Yeah. Okay. Well, thank you, Nicholas. And it's a pleasure to be back in Cambridge. I spent some of my formative time intellectually here, and it's just great to be back. So I'm going to talk a little bit about work that I have done with the Event Horizon Telescope collaboration. And a large part of this work is presented on behalf of my colleagues in the Event Horizon Telescope collaboration, so over 300 people. And other parts describe work that I've done with my students, including the ones you see listed here, and a couple of others, including Boris Georgiev, who's now a postdoc at Arizona, and Avery Broderick, who's at Perimeter Institute. Okay, so here's the plan. So I'm going to start by reviewing some of the Event Horizon Telescope results, and then I'm going to describe how we go about modeling Event Horizon Telescope sources. So this is primarily what I do. I build models, and then we work to compare those to the data. Then I'm going to give you a description of the future of black hole imaging. So we think that there's an exciting future ahead with upgrades to Event Horizon Telescope and possible space-based elements to the array of telescopes that's used to image black holes. And then I'm going to wind up, if there's time, with a discussion of a prediction that we're making for future Event Horizon Telescope observations, which involves hotspots around black holes. All right, so now I'll go to describe the Event Horizon Telescope results. I think most of you have seen this image. So our collaboration outreach people estimate that about 4.5 billion people have seen this image, which is pretty good for an astronomical image. Before I tell you what you're seeing in this image, I want to talk a little bit about how the image was made. It is derived from very long baseline interferometry data that's taken with a network of millimeter telescopes spaced around the globe. And at each of these telescopes, there's a special VLBI equipment rack, which includes a precise clock and stacks of disk drives to record the voltage stream coming off the telescope. And then those voltage streams are later correlated at a central facility. And that correlation gives us Fourier amplitudes that correspond to individual pairs of telescopes. And it also tells us about other properties of the source, certain combinations of phases in the source, which can then be used to attempt to reconstruct an image. So this shows, or will show, some of the sites that were used in the Event Horizon Telescope observations. And then we'll show you some of the baselines that are used. And you can think of these baselines as representing Fourier components. So each one represents a wave vector that's sampled by the observation. Okay, so as the world turns, we begin to gather information from individual baselines, and then those are assembled into an approximate image of the source. And this shows what happens as you add in individual phases and Fourier amplitudes in the construction of an image. So at the end, it's possible to take an image of something as small as a teapot orbiting between Earth and Mars if the temperature of the teapot is about 10 to the 10 Kelvin. So you can see that at first, with just a few baselines, which was what was available to early instantiations of the Event Horizon Telescope, you can't really construct an image, but you do get some information about spatial structure of the source. And then as you add in more sites, and especially ALMA here, you get higher sensitivity and more information about the structure of the image. So the image that I just showed you is constructed from this 1.3 millimeter VLBI data taken in a 2017 campaign. So in the late spring of 2017, people fanned out to all these telescopes, 8 telescopes at 6 sites, and over the course of about a week took the relevant data, petabytes of data. Those disk drives were then carried back to a central facility and correlated. Okay, so that gives us this image of the black hole at the center of M87. And this image, you should understand, is a non-unique representation of the data. So in sampling in the Fourier domain, we cannot sample all the points in the Fourier domain, so we have to make assumptions about the amplitude at unsampled points in order to construct a full image. And so certain features of this image are strongly constrained by the data and other features are not. So for example, this asymmetry here is well constrained and the radius or diameter of the ring is well constrained, but other details are not. So this secondary peak here in the brightness is possibly an artifact of the data, of the reconstruction technique. Okay, so what you are seeing in this image is 1.3 millimeter radiation from a hot plasma that surrounds the black hole. And this radiation is produced by the synchrotron process. So there's, we believe from modeling, sort of Lorentz factor 10 to 100 electrons in a few tens of Gauss magnetic field that's producing the observed radiation. And to give you a sense for the size of the object that we're looking at, I have here a convenient image from XKCD, which compares the black hole itself with the size of the solar system. So here's Pluto's orbit in there, and there's Voyager 1. So the object that's being resolved here is extremely large compared to the solar system and extremely small compared to the galaxy M87. All right, so what can we measure from this? What science can we do with this? Well, one thing that can be done is to measure the diameter of this apparent ring. And if we believe that this ring corresponds to the edge of the lensed image of the event horizon, then we can calculate directly what the angular size of that image should be in terms of the mass of the black hole and in terms of the distance to the black hole. So it's exactly, should be exactly root 27 times this characteristic linear scale divided by the distance. So if there were no gravitational lensing in the neighborhood of the black hole, then the size of the image would be either 1 or somewhere between 1 and 2 times this characteristic angular scale. But because of gravitational lensing, the black hole appears larger on the sky than that naive estimate. And by a factor of almost 5. So absent gravitational lensing, it would not be possible for Event Horizon Telescope to resolve the source. Okay, so this gives us a relationship between this measured angular diameter and the mass of the black hole and the distance. Given the distance, we can then use this to estimate the mass, and that tells us that the mass of the black hole is about 6×10⁹ solar masses. And to put this in context, at the time this observation was made, the mass of the black hole in M87 was uncertain to about a factor of 2. And so there were a set of measurements that indicated that it was about 6×10⁹ solar masses. And those were from stellar kinematics. And then there were another set of measurements based on gas kinematics that suggested that the mass was closer to 3×10⁹. And so had the gas kinematics estimate been right, we would also not have been able to resolve this source. So we were very lucky that the stellar kinematics estimate turned out to be right. Okay, so M87, as you may remember, is the archetypal extragalactic radio jet source. And this ring lies directly at the base of the jet. And so this shows over many orders of magnitude in scale, starting with this 1.3 millimeter ALMA image, and then moving down in scale to the scale of the event horizon. This relationship between the jet itself and the black hole at the base of the jet. One observation which is not in this set of images is a recent 86 gigahertz observation using the GMVA, the Global Millimeter VLBI Array, which shows both the ring and the jet in the same image. And so we know that there's now a direct connection between this ring and the jet itself. So this first image of a black hole tells us that the black hole is at the base of the jet, and it's reasonable to conclude from this that the black hole, or the material around the black hole, powers the jet. So this is consistent with hypotheses that have been around for decades, and consistent with work that was done by Blanford and Znayak here in the 1970s, suggesting that the extragalactic jets are powered by extraction of rotational energy of the black hole using magnetic fields. Okay, so this was the image that came out in 2019. In 2021, we were finally able to process the linearly polarized data, and we were able to produce the first polarized image of a black hole. And these streaks here indicate the direction of the electric vector polarization angle on the image. And these streaks show or are consistent with a structure for the magnetic field close to the black hole, which is a spiral oriented with the field oriented perpendicular to each of these streaks. So in synchrotron radiation, there's a characteristic direction given by the magnetic field, and the electrons move around the field line and produce polarized radiation, linearly polarized radiation that tends to be perpendicular to the magnetic field. So in a naive model, which doesn't include any of the gravitational lensing or other important effects, we're simply looking at the direction of the magnetic field here. So it's consistent with a spiraled, trailing spiral magnetic field oriented in this direction. Okay, so that was 2021. In 2022, the collaboration managed to finally understand what was going on in the galactic center. So we have 2017 data of the galactic center, and we were able to assemble an image of the galactic center black hole. And it looks like this. It's very similar to the M87 black hole. The M87 black hole is 6×10⁹ solar masses. The galactic center black hole is 4×10⁶. So it's a factor of about 1,500 lower in mass, but also a factor of about 1,500 closer to us. So it appears to be almost the same size on the sky, slightly larger. So Sagittarius A star is much more difficult to study because it changes rapidly. It changes on a characteristic timescale of minutes, as opposed to M87, which is much larger and changes on a timescale of days. So because it's changing on a timescale of minutes, it violates one of the fundamental assumptions that one uses to do imaging in VLBI, which is that the source is not changing. And so it took a substantial amount of effort to construct a procedure which would produce a time-averaged image of the source. So I want to emphasize that this is a non-unique representation of the data, and that there are likely to be more artifacts in this image than in the image of M87. So in particular, you see these 3 bright spots on the ring, and it looks kind of like the Ubuntu logo, if that means anything to you. But those may well not be real. So, so you shouldn't try and interpret those. What you can interpret is the diameter of the ring. And again, we can use that to measure the mass. In the case of the galactic center black hole, we know very well what the distance is. And so the errors in our mass estimate derive largely from uncertainties about our model for the source and in our limited coverage of the Fourier domain in making the image. So in the galactic center, the diameter of the ring is about 52 microarc seconds, and that implies a mass of about 4×10⁶ solar masses. And this is consistent with the measurements of the mass of the black hole in the galactic center by Gase and by Gensel using stellar orbits. So this tells us that, first of all, that there really is something that looks like a black hole there in the middle, and it tells us that the mass of that thing is about the same as the mass measured at thousands of gm/c², thousands of Schwarzschild radii from the black hole by the orbiting stars. Okay, so those are some of the highlights of the Event Horizon Telescope results so far. And to say more, I've got to talk a little bit about the modeling. So now I'm going to give you a quick tour of modeling of Event Horizon Telescope sources. Okay, so first of all, you can ask what shapes the EHT image. So what is the physics that determines the structure of those rings? And there are 3 things that are particularly important. One is gravitational lensing, as I've already alluded to. So in the image on the ring, we can trace back lines of sight that land on the ring. And if we're just inside the ring, the lines of sight go back onto the event horizon of the black hole. And if we're just outside the ring, the lines of sight go past the black hole and are deflected we're deflected on their way to us by the black hole. Sometimes extremely deflected. So there's some small fraction of the light that we see which involves photons that have circulated around the black hole multiple times, but only a very small fraction of the light. Okay, so lensing is important. The plasma flow is important. So one of the things that my group does is model the plasma flow around the black hole. So we build large numerical models and of an ideal fluid around the hole, and we evolve those on supercomputers, and then we observe them. The final element of the physics that's important is the plasma physics, and in particular, the distribution of electron energies, because it's the distribution of electrons over energy that determine the emissivity and absorptivity of the plasma around the black hole. And they also determine how the polarization of the light changes as the light propagates through the circumbothric plasma. Okay, so let me describe each of these things in turn, and I'll start with our state-of-the-art models of the black hole. So let me show you a little illustrative image. So this was courtesy of some 4th and 5th graders at our local primary school. And they have a black cloth in the middle, which is meant to represent the black hole. And we bought a drone just to do this, actually. So this is taken from a drone. So there's a black hole in the middle, and then the students are meant to represent the electrons and ions and possibly positrons circulating around the black hole. And you can see that they're, at least in this model, circulating primarily in one direction, and then every once in a while one of them accretes, but only on a very long time scale. So this plasma is accreting only very slowly onto the black hole. I have a movie that I won't show you of the Hawking evaporation of the hole at the end. So these students are actually fairly collisional. The mean free path for the students is some tens of event horizon radii, whereas in reality, in the plasma around M87 and Sgr A, we think that the mean free path is maybe 100,000 times the size of the horizon, and that's a key uncertainty in the models. Okay, and there's me saying everybody accrete now. Okay, so this is what we're modeling on the computer. So we put fluid into circulation around the black hole, and we seed it with a magnetic field, and then we turn on the simulation and watch it accrete. And we start with a torus at finite distance from the black hole, and we think that this might be okay because most of the emission comes from very, very close to the hole, within a few Schwarzschild radii of the event horizon. And so perhaps what happens further out is not important, although this has been a point of some contention in the community. Okay. You see, one other point about this is that the circular velocity of the students is constant here. Okay, so that's not like accretion onto a black hole where they should be moving faster at the inside. Okay. All right. So then we build these computer models, something like this, of flow around the black hole, and then we image them. And when we image them, we trace the photon geodesics out to a synthetic camera and build an image. And again, the situation is what I described a little bit earlier, where if you're looking directly at the center of the so-called shadow of the black hole, the lines of sight trace back to the event horizon. And then as one goes out to this critical impact parameter, one approaches the so-called photon orbit. So if I'm exactly at that critical impact parameter and I trace the trajectory back, I wind up on the photon orbit around the black hole. And then further out, there's deflection of the rays by the gravitational field of the black hole. So this is gravitational macro lensing. All right, so here's sort of a summary of what's done in these models. We have a simulation, a magnetohydrodynamic simulation. We have to assign an electron distribution function to it, and because that's somewhat uncertain, we have a parametrized form of the distribution function that we can scan over, one parameter distribution. Then we do a radiative transfer calculation, and at the end of the day, we can predict everything. So we have full Stokes as a function of frequency and position on the sky and time. Okay. So the result of all that is at 230 gigahertz at the wavelength that's observed by EHT, something that looks like this. Okay. So this is a fairly typical model. This is one of the models of the galactic center black hole that is almost entirely, but not quite entirely consistent with the data. And you can see that critical impact parameter here in a very narrow ring. We don't get to see that in the observations because our resolution isn't high enough. And then you can see there's material sort of circling the drain here and going into the black hole. So not only can we make movies of a source like this, but we can also calculate the spectrum. And so we can use multi-wavelength data to constrain the models. And this shows a spectrum up here as a function of frequency on the horizontal axis. So the EHT data is taken here. This is the 86 gigahertz data. And then the 2 micron observations of the galactic center are done out here. And in this particular model, this first bump is the synchrotron bump, so that's synchrotron radiation direct synchrotron radiation from the plasma. And then we have the first Compton order here. So these are singly scattered synchrotron photons. All right. So this allows us to build a library of models and then compare that library of models to the data and then try and constrain the model parameters using both the EHT observations and data at other wavelengths, which is not resolved. Okay, so this is meant to show you something about our library of models, a very large library of possibly wrong models, but we think the best models that we're capable of producing at the moment. This shows a set of models at the top half, which are so-called MAD models. So these are magnetically arrested disk models. In these models, magnetic flux accumulates on the black hole until it is as large as it can be without pushing aside the accreting plasma and escaping. And so in these MAD models, the magnetic flux tends to saturate at a particular value. The sane models are the opposite of those. So that's the lower half of this image. The sane models look more like conventional accretion disks. Then there are a number of other parameters represented here, including the spin of the black hole, the electron temperature parameter, and the inclination of the source on the sky. So then we can let this go. And you can see, there are many models, but they all look slightly different. And if we apply a size constraint from Event Horizon Telescope, we can eliminate a small set of the models. If we then apply a shape constraint, we can eliminate many of the models. The spectrum kills off a few more. And then a constraint from the low frequency, meaning 86 gigahertz size of the source, leaves us with just 2 models in this library at the end of the day. All right. So the final set of models are MAD models. They're strongly magnetized models. They don't look like conventional nearly circular orbit accretion disks. They're extremely unsteady. And most of the accretion occurs through sort of elephant trunks of plasma that are lowered toward the event horizon using on-magnetic field lines. The models that are left are also rapidly rotating and nearly face-on. So we can eliminate the nearly edge-on models for the center of the galaxy because they look quite different. There's a number of Doppler beaming effects that change for example, the infrared radiation from the source as the disk is made to be edge-on. So again, at the end of the day, we have a population of relatively cool electrons, nearly face-on, MAD models, spin greater than about 0.5. So whether this actually means that the galactic center black hole has a spin of 0.94 or not is unclear. But what I think you should take away from this is that there is a power to constrain the models in the observations, and that some of these models can still explain most of the data. What they cannot explain is the variability of the source. So the one fly in the ointment is that the models, these successful models, are slightly more variable in the millimeter than the observations. So the observations measured on a 3-hour timescale have a relative variability of about 7%, and the models have a relative variability of about 14%. And we're very interested in chasing this down, but that's the only fly in the ointment at this point. Okay, so here are the results of this sort of set of model comparisons between GRMHD models and the observations of M87 and Sagittarius A star. So the measurements of the mass depend on the models because they tell us, the models tell us where to put this critical impact parameter on the sky. Does it go at the inner edge of the shadow, the outer edge of the shadow, or does it go further out in the ring? So this allows us to estimate the black hole mass, and for M87 gives us an uncertainty of about 20% in the black hole mass, which again was previously uncertain to about a factor of 2. For the galactic center black hole, we find a mass that's consistent with Gaze and Gensel, again with an error of about 20%. And much of that error, again, comes with comparison of the with these sort of these blurry rings with these models. So we don't know exactly where to put the so-called critical curve on the sky. We've confirmed that there's a black hole at the base of M87's jet, and it's a feature of the model, of all the models, that only non-zero spin models, so Kerr black holes, produce substantial jets. We find that models with spin 0.5 and above produce jets which are consistent with the data. And this is consistent, again, with the Blanford-Znayak hypothesis. And then there's a set of other conclusions here. Comparing over this model space, we find that the magnetically dominated models are strongly favored for both M87 and for Sagittarius A star. So the conclusion there that you should take away is that it's a mad, 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 mad world. We also have information about which way the spin vector of M87 is pointing. And that comes from the asymmetry that you saw in the ring in M87. So we think that the asymmetry is controlled not by the motion of the plasma in the disk, but by the spin of the black hole, which controls emission from the immediate neighborhood of the jet. And that suggests that the spin vector is pointed away from Earth. We also find that Sagittarius A star has an accretion flow inclination of less than 70 degrees, again, with the proviso that you need to believe the models. And then finally, we have this mystery, this variability crisis. Sag A star is quieter than expected from the models. Okay, so now I have this quotation from Feynman that I love to put up, which says, we're not used car salesmen. We should talk about the sins we've committed in creating a model and expose ourselves to criticism. So here are some limitations of these models. So probably the most serious is that the plasma is approximately collisionless. So that means that the mean free path to Coulomb scattering of the ions and electrons is large compared to the size of the black hole. And we're using an ideal fluid model, which is a short mean free path approximation for this plasma, which clearly has a long mean free path. So how this affects the models is somewhat unclear. And one possibility is that the fluid is effectively collisional because of kinetic effects. So there's an idea which is described as fluidization, which says that in the process of evolving, the plasma drives what are called kinetic scale instabilities, so small scale instabilities, which excite small scale fluctuations in the electromagnetic field. And those small scale fluctuations then scatter the ions and electrons and provide an effective collisionality. We don't know if that's true yet, but there's a whole, actually now that there's a Simons Center for working on this, there's a lot more people studying this than there used to be. So there's a whole group of people doing particle and cell simulations to study the relevant dynamics. And I think there's reason to hope that within the next few years we'll know whether the ideal fluid model is adequate or not. We also use a thermal model for the electron distribution function. And I think everybody here has taken radiative processes, and you always learn that synchrotron is a non-thermal process. But what we do in all these models is use a thermal distribution for the electrons, which has a characteristic temperature of order 10 to 30 in electron rest mass units. And that may not be adequate. We do know that if we put too large a non-thermal tail on the distribution function, then the models don't work because they overproduce emission in the near infrared. So there are constraints on the distribution function. But whether this thermal model is accurate enough is still unclear. We also use an approximation that the local thermodynamic state of the plasma controls the electron distribution function. This is a little bit technical. So this just means that the plasma is assumed to adjust instantaneously to local conditions, and that may not be the case. Finally, the models depend on the boundary conditions. And just to give you an example of what this means, in the galactic center, it's believed that the black hole is fed by winds from the surrounding stars. And those winds propagate toward the black hole and may not have an opportunity to circularize before they accrete. And Sean Ressler and Elliot Quadiert and others have worked on this problem and produced models that follow the plasma all the way from those stars orbiting at thousands of gravitational radii, Schwarzschild radii, down to the black hole. And the result of that is models that look very, very much like the models that we produced from initially circularized plasmas. So we included those in the comparison between the models and the data. Finally, there's some initial condition dependence, and then we all use something called the fast light approximation, in which we take snapshots from the simulations and make images from individual snapshots on individual time slices. And of course, what we really should do is track the photons back through the simulations as they evolve and include those finite light crossing time effects. But so far, at least for the model comparisons we've done, there's no evidence that that makes any difference to the comparison. Okay, so next up, just a little bit about the future of black hole imaging. So part of the future of black hole imaging is already in the bag. So the Event Horizon Telescope has taken data in campaigns in 2017, 2018, a bit of a gap for the pandemic, 2021, 2022, and 2023. And what's been published so far is data from this first campaign in 2017. So we've published total intensity data, we've published linear polarization data, and in just a couple of weeks, the circular polarization images will be coming out. In the near term, in about 2 months, we'll see the total intensity data from 2018, and you'll be able to see whether it's consistent with images from 2017. So as time goes on, these campaigns, and this column here lists the telescopes that were involved, the new telescopes have been added to the array. And this means more complete sampling of the Fourier plane. So we can produce higher fidelity images as time goes on. And in 2018, we added GLT. So there's a key down here that helps you read these 3-letter codes. We added a Greenland telescope, which is at Thule in Greenland. It's a joint effort of Asia A and Center for Astrophysics. And that produces a set of nice north-south baselines, which fill in places in or parts of the Fourier domain that were not covered before. So we're excited about the 2018 data. And then again, as time goes on, we've added NOEMA. This is Kitt Peak, and this is the large millimeter telescope in Mexico on a volcano in Mexico. So what you can expect to see over the next few months and years is the results of this data, which will have higher imaging fidelity and will be able to confirm or refute the earlier sets of images. Okay, in addition to this, there are plans to expand the capabilities of the EHT array, and some of these are already underway. One important improvement is to go to higher frequency, to 345 gigahertz. So right now, the observations are made at 230. By going to 345, shorter wavelength, we can obtain a higher angular resolution with the new images. This is very difficult because most of the sites are not capable of doing 345 gigahertz imaging. But if we get enough of them to 345, then we can move the nominal resolution of the telescope from 20 microarc seconds to 13 microarc seconds, which is a significant improvement. So this is already underway. There's 345 gigahertz fringes have been detected, and more sites will have 345 gigahertz capability in the near future. Another new capability is so-called agile observing. So the idea is to structure the array so that it can revisit a source every few weeks. So in particular, for M87, which only changes on a relatively long time scale, we can go back and take snapshots every few weeks and make a movie of the black hole. So that is coming. And then, and this is somewhat more speculative, there are lots of new sites that are being proposed or constructed. So the African millimeter telescope is underway. So there's funding for that that's been identified. Rob Fender over at Oxford is involved in this. Sarah Markov is another one of the PIs, and Heino Falke at Radboud is another one of the PIs. And this site is in Namibia on a mountain that's been used before by the Max Planck Society to do observations. There's also a proposal for something called the Next Generation Event Horizon Telescope, and that will build as many as 4 new sites. And once all these elements are in place, assuming they all are funded, then we'll be able to cover about 70% of the accessible part of the UV plane of the Fourier domain. Another even more speculative possibility is going to space. And a number of us are involved in this. The idea is to put a satellite, possibly a geosynchronous orbit, possibly multiple satellites, Instead of, the strategy here is to go to shorter wavelength to increase the resolution. The strategy here is to go to longer baselines. And that could potentially push the resolution of the instrument to as little as 5 microarc seconds. And one reason that's particularly interesting is because it would enable us to detect that very narrow feature associated with the critical curve on the sky. And that would allow a very precise measurement of the black hole mass. Okay. I'm used to being interrupted, but thank you for your politeness. So now I want to talk in just the few minutes I have left, and I'll only spend a few minutes on this, about a prediction that arises from the models that we built for Sgr and for M87 star. And in particular, we're interested in understanding what movies might tell us about the black holes. And if you've worked in black hole accretion for a while, you've heard of hotspot models. And in hotspot models, you imagine that there's a bright lump of plasma, a blob, I think is the term of art. And this blob orbits ballistically around the black hole. And as it goes, it gives up the characteristic frequencies of the orbit. And that's a very appealing picture because it allows you to connect the observations directly to the space-time. So we can ask whether the models, as they've been constructed so far, produce hotspots. So what do the models predict? So here's the hotspot model. I've taken the image of the galactic center and put a hotspot into orbit around the black hole. By the way, these are also the models that are used to interpret the gravity data from Genzel's group. So this is a near-infrared interferometer that allows one to do astrometry on the flares associated with the galactic center source in the near-infrared. And those seem to, at least in some instances, have a little bit of rotation around the black hole. Okay, so here's a caricature, and then here's one of the simulations. And if you look at this, you can see a number of different frequencies present in the model. So there are a few things that look like they're moving very quickly around this ring. And there are other features, some of these spiral features, that look like they're moving rather slowly around the ring. And if we had access to this set of images, then we could sort all that out. But we don't get to see this. We get to see something that looks like this. Okay, so a much lower resolution image. And we'll have maybe 10 frames of a movie. So it's not going to be a feature-length film. And if you look at this, you can see some circulation of the bright spots around the ring on the sky. Now I'm going to show you what happens if you superpose a clock hand with the orbital frequency of the plasma at the radii where this emission is produced, which is sort of 2 or 3 Schwarzschild radii. Okay, so this is what it looks like. This has been designed to actually move not with the orbital frequency, but slightly less, which is the frequency with which the plasma orbits the black hole. Okay, this looks too fast to me. Instead, we can go into this movie and using an autocorrelation technique, extract a characteristic pattern frequency for these bright spots moving around the ring. And that gives us a pattern frequency which is approximately an order of magnitude lower. So you can see here, there's some small features which move very quickly, but the dominant features are these larger, brighter spots that are moving more slowly. And those, again, to go back to the movie, Now we have the rapid clock. To go back to the movie, are these spiral features that you can see crossing this critical curve on the sky. So this shows the rapid clock hand, and this shows the slow clock hand. Now, this might be an artifact of something that we've unconsciously built into the models, but at the moment, it's the best prediction that we can make for the pattern frequency on the sky. And in particular, one thing that we do know is that it's not got to do with the resolution of the simulations, because we can build a model with twice the linear resolution and get exactly the same pattern speed to within 1%. Okay, so that's it. So just to summarize, review the Event Horizon Telescope images. There's some nice results that come out of this. And I think the most significant is that there's a black hole at the foot of the M87 jet. So this looks like very strong evidence that the jet is powered by the black hole. We have built a whole set of models of EHT sources. These are the best models that can be constructed at present. They're the best models that we can construct that can be directly compared with the data, which is a huge leap for many of us doing astrophysical simulations. Often our models can't be directly compared with the data, so it's nice to be able to do so. There's a bright future in imaging black holes. So there's lots of data in the can that's being analyzed now that will have fuller UV coverage than the 2017 data. And then we will soon have movies. And then finally, the models predict slow, non-ballistic circulation around the ring from the movies. That's it. Thank you.